So we're looking at Lewis dot structures, and we've already gone over all of our rules. We're going to use those rules to determine the structure of various compounds. So we're going to start off by doing ammonia, nh3. And the first step is we need to figure out how many valence electrons ammonia has. Nitrogen, there's one nitrogen, and nitrogen has 5 valence electrons, and so we end up with 5 electrons. For hydrogen, there are 3 of those guys, and each one is 1 electron, so we end up with 3 electrons. You add them up, we get 8 electrons in this figure. And we're going to follow the next rule of putting the least electronegative in the center, the H's always go on the outside. Then we connect them up with our electrons, 2 of them at a time. 1, 2, 3, 4, 5, 6. So we've got 6 electrons that we use just by connecting everything up. Now, we can go up to 8. So now we have to analyze the molecule, see where we need to add the electrons. The hydrogens are fine just when they get added. When they get connected to something, they are good and they are happy because hydrogen only needs 2 electrons. So that's good, that's good, that's good. Nitrogen needs 8. 1, 2, 3, 4, 5, 6. So we're going to continue. We've got 6 in there. 7, 8. 8 is the maximum number we can get in there. Now nitrogen has 8 and it is happy as well. If we want to rewrite this, or we want to write this with the lines, we can do that. So we can write it with the N in the center and the lines connecting all of the hydrogens. But remember, you need the Lewis dot structure, you need the lone pair for making that Lewis dot structure. There are times when we do write nitrogen without the lone pair, but that is not a Lewis dot structure. So this would be okay, this would be okay for submitting a Lewis dot structure, but not that one. Okay. Get all those lone pair or non-bonding electrons in there, and that way you'll make sure that you have a true Lewis dot structure. Let's go ahead and do the next one. The next one is carbon dioxide, so CO2. We'll again start off with counting the valence electrons. Carbon, there's 1 of them. 4 valence electrons each, so you've got 4 valence electrons. Oxygen, there's 2 oxygen and 6 valence electrons each, which gives us 12 electrons. And when we add them up, we get 16 electrons. So this whole thing can have exactly 16, no more, no less. So let's go to the next step. We write the least electronegative in the center, the other guys around it, and then we have to connect everything up. 1, 2, 3, 4, we added 4 valence electrons to this figure just by connecting everything up. We can get up to 16, so we have a ways to go. And we look at, to know where to put them, we analyze our molecule. Well, this guy doesn't have 8, this guy doesn't have 8, that doesn't have 8. So we've got to add it across the board and count from 4 up to 16. So let's go ahead and do that. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, now we're at 16. We cannot add any more dots. Okay? So we have the maximum number of dots already on the screen. Let's go ahead and see if anything's happy or what's not happy. This guy has 1, 2, 3, 4, 5, 6. The oxygen's not happy. So we need to do something about that. Carbon has 2, 4, 6, 8. It is happy. And this oxygen is just like the other one. It only has 6. So the oxygens is where we've got to do some work with. Well, let's see. This oxygen's not happy. So we can move the electrons to adjacent molecules. And that's this 5th rule down here. We can form double and triple bonds if we need to, if we run out of electrons. So let's go ahead and move these electrons. And he's going to come next door, and he's going to ask carbon if carbon will share with him. Because if oxygen shares its electrons, it's not going to help oxygen out, because it's going to keep them, and then carbon gets too many. But it can come next door and ask carbon for some. Carbon will keep the electrons, but it gets to share them. So carbon still has 8, but now oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Because now it's sharing those electrons down there. So now this oxygen is happy, fulfills the octet rule. We can do the same thing with this guy over here. He's not happy. He can come next door and say, hey, carbon, can you help me out? Carbon says, sure, I'll share my electrons with you. And so now, oxygen over here has 1, 2, 3, 4, 5, 6, 7, 8. Fulfills this octet, it's happy. Now keep in mind, the carbon didn't lose anything by sharing. It still has 1, 2, 3, 4, 5, 6, 7, 8. It did not lose anything by sharing. It just let oxygen share some of its electrons. And of course, we can rewrite this with the double bond in there. This is not a Lewis dot structure, though. Remember, we need the lone pair, the non-bonding electrons in there, in order for it to be a Lewis dot structure. Now it's a Lewis dot structure. Either one of these would be correct answers. All right, let's do one more over here. We'll do carbon tetrachloride. Okay, add up the number of electrons. Carbon, there's one of those, 4 electrons each, so we get 4 electrons from carbon. Chlorine, there's 4 of those. We get 7 electrons from chlorine because it's a halogen, and so we get 28 electrons overall. No charge, so we just add them, and we end up with 32 electrons in the figure for this carbon tetrachloride. We put the least electronegative in the center, the more electronegative on the outside. We connect them up with bonds. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons have been used just to connect things up. We need to get up to 32, so let's analyze it, see where exactly we need to add those electrons. Carbon is happy. 1, 2, 3, 4, 5, 6, 7, 8. Carbon is good. It's got all 8. So we're going to leave carbon low. Chlorine, on the other hand, only has 2. We see that all the chlorines are in the same position. They need more electrons. So as we count from 8 up to 32, we're going to focus on putting them on the chlorines. Okay? So we've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Oh, that's where we've got to stop, 32. Now let's double check. Our carbon is still happy. It's got 8. Let's check our chlorine. 2, 4, 6, 8. Chlorine is in fact happy. You can see that all the chlorines look the same, so they all have 8. So this is the structure for carbon tetrachloride. Again, if you'd like to write it with the bonds, don't forget they need the lone pair. If you don't have the lone pair on there, it's not a Lewis dot structure. All right? So either one of those would be good for a Lewis dot structure, like carbon tetrachloride. All right, there's one more thing that we want to talk about. So far we've talked about molecules that have a central atom. Okay, you put the least electronegative in the center, everything else goes around the outside. Well, there are some cases in which that may not be the case. Say, example, we've got CH3, CH2, COOH. Now, you might ask, well, why didn't you write it C3, because there's 1, 2, 3, H6O2? And the reason why we write it this way is because we want to convey some type of connectivity, how these atoms are actually connected to each other. So anytime you see them written out side by side like this, it's telling you something. And let me explain how this goes. So with this one, anytime you see the CH3, it means that there's a carbon and it has 3 hydrogens on it. So we're going to write them H, H, and H. Then this carbon is attached to the carbon next door. Carbon. And that carbon has 2 hydrogens on it. So we're going to put an H up there and an H up there. And that carbon is connected to the to the carbon next door. We're going to put the carbon there. This carbon is attached to that oxygen. We're going to stick that up. It's also attached to an OH group. So we're going to put O and an H out there. So this representation is actually telling you that this is what's going on. Now this is not the final structure. We still have to count up valence electrons. Okay? This is just the connectivity. So let's go ahead and go through our whole method of doing Lewis dot structures. I'm going to use this condensed version of the formula to count up our valence electrons because it's a little easier. We've got carbon. We have 3 of them. Each one has 4 valence electrons, so we have 12 electrons from there. Then we have hydrogen, which is 6 of them, 1 electron from each one. We have 6 electrons there. Oxygen, there are 2 of those, and we have 6 valence electrons from there. So we have 12 electrons. We add these all up, 24 plus 6, we end up with 30 valence electrons in this molecule. So let's go ahead and see how many we use just to connect things up. Remember, each line is actually 2 electrons. So 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. We use 20 electrons just to connect everything up. So we still have some more. We've got 10 more that are needed to be added to make the structure of Lewis dot structure. So let's look at where we need to focus to get this guy happy. Okay, the H's are all happy just by connecting them. This carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. Those are both carbons that are happy. This carbon only has 6. 1, 2, 3, 4, 5, 6. So we need to focus in on that one. The oxygen only has 2, so that needs help. And the oxygen over here has 4, so it needs help as well. So we're going to focus on this part of the molecule and add the electrons from 20 up to 30. Okay, so let's go ahead and do that. 1, 2, we were at 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We are done. We can't add any more. 30 electrons. Okay, now let's analyze this again. Make sure that everyone is happy. We said that part of the molecule is happy. We didn't touch it. So it's still happy. If we touched it and moved things around, we'd have to go back and check. But we didn't, so that's good. The carbon here, 1, 2, 3, 4, 5, 6, 7, 8, it's happy. Okay, good to go. This oxygen though, 1, 2, 3, 4, 5, 6. Oh, it's not happy yet. Let's check the other guys. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8, it's happy. All right. So it's this oxygen that's still not happy. So he's going to go next door and say, hey, carbon, can I borrow some of your electrons? Can we share? Carbon says, surely. I'm a good, nice neighbor. We're going to share. We're going to put those 2 electrons in between. And now carbon can still count them as their electrons. So carbon has 1, 2, 3, 4, 5, 6, 7, 8. But oxygen can count them as their electrons too. 1, 2, 3, 4, 5, 6, 7, 8. So now everything's happy. We've got the 30 electrons shown in this figure. All right, let's see if we have time before our video closes out to do one more. If there's a molecule like h2o2, and this is hydrogen peroxide, looks similar to water, but it's not. So if there's a molecule like this where you don't necessarily have connectivity told to you, you'll be given that connectivity so that you can do the Lewis dot structure. Okay, let's start off with number of electrons. So H has 2 of those guys. Each one is 1 electron. So we've got 2 electrons there. Oxygen, there's 2 of those. Each one is 6. So we've got 12 there. This figure is going to have 14 little dots on it. So the connectivity is that H is connected to O, which is connected to the other H. So that I would have to give to you in order for you to do this particular structure. So let's go and connect everything up. 1, 2, 3, 4, 5, 6. 6 electrons just to connect everything up. Let's finish this guy up. We can go up to 14. The H's are happy just by connecting them. So 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, we've reached our max. And that's as far as we can go. Let's see. The H's we said were happy just by connecting them up. Let's look at the oxygens. 2, 4, 6, 8. That oxygen is happy. 2, 4, 6, 8. This oxygen is happy. So we've got the central atom surrounded by other things that you can do Lewis dots for. You can do Lewis dots for ones where I give you the connectivity, and you can do Lewis dots for like those long connected carbons and hydrogen molecules, which you know how to read now. You see those,